Hello, everyone, and thank you for joining us today. My partner, Dariana Martínez, and I, Ana Isabel Boyd, will talk a little bit about our poster number 3640 titled Reuse of Plastic in Geogrids for Unpaved Roads. Our work team is comprised of four civil engineering students, including Dariana Martínez, Mónica Flores, Orlando Leyva, and I, along with our research advisor, Dr. Francisco Grajales. More than 4,300 tons of trash is produced daily all over Panama. Approximately 5% of the total amount of plastic is recycled. The rest is either stored, sent away to other countries, or simply remains as garbage. Given the low recycling percentage, reusing should be practiced more. In Panama, unpaved or gravel roads are often used in rural regions of the country, where the amount of traffic does not necessarily justify the investment of a paved road. Even so, it is important to highlight that in most cases, these roads are important for transportation of agricultural produce as well as the transit of tractors and agricultural machinery, the latter producing significant damage to gravel roads due to the weight. There are over 3,000 miles of unpaved roads throughout the country that could benefit from having a type of reinforcement to avoid possible accidents. In the United States, there are approximately 1.4 million miles of unpaved roads, equivalent to 35% of the roadway system in the nation. The general objective of this investigation is to assess if plastic waste can be reused as raw material to create a type of geogrid that could be implemented in unpaved roads. Geogrids are geosynthetic materials that are used in the construction industry in the form of a reinforcing material. They have the purpose of holding or capturing the aggregates together. The apertures in geogrids help to interlock the soil or aggregates that are placed over them. The interlocking of the aggregates increases the frictional resistance in the interface, which mechanically stabilizes an earthwork. Geogrids can provide a separation to a certain degree between the base and subgrid materials and their reinforcements. This prevents the mixing of subgrid soil and granular base materials, which tends to deteriorate the base cores over time. Surface rutting is mostly caused by two main factors: compaction of base cores aggregate under repeated traffic loading and bearing capacity failure. Non-reinforced unpaved roads tend to exhibit a phenomenon known as rutting, which involves the formation of depressions produced by repeated pass of wheels. Deep ruts can cause mixing of the base course material with subgrade soil, thus producing a decrease on the mechanical performance of the gravel. If the mixing is severe, the base course may require complete replacement, which may have an elevated cost. Geogrid reinforcement can be used to prevent or reduce rutting. The base course should be able to interlock with the geogrid's apertures. In such case, the geogrid may be able to prevent the lateral movement, which reduces surface rutting. Vertical strains are reduced and shear strength is increased, which increases bearing capacity of subgrade and helps prevent shear failure.
Work methodology. Scraps and pieces of polypropylene, low-density polyethylene, and high-density polyethylene were used in this investigation. Two geogrids were made from each type of plastic as prototypes. Table 1 shows the ultimate tensile strength of each material. With an ultimate tensile strength of 13.8 to 460 megapascals, polypropylene strands are expected to resist more tensile force. 10 strips of each type of plastic underwent tensile stress testing in accordance with requirements of ASTM D638-03, a standard test method for tensile properties of plastics. The video display shows an example of a polyethylene strip being tested at the facility. Results from this test are compared and could work as a baseline to make further investigations about the topic. Experimental results. Results were processed by dividing the resulting force of each element in kilonewtons by its respective distance in meters, from the bottom pincer to the top pincer of the machine. Maximum tensile strength achieved per material are shown in Table 2. Polypropylene samples achieve a maximum tensile strength of 6.08 kilonewtons per meter. Results are presented in figures 1 to 3. There is a noticeable amount of scatter in the data. which is believed to be due to the somewhat improvised fabrication procedure of each strip. Polypropylene results are compared with the national and international Geogrid market, as seen in Table 2. It is important to emphasize that these results show tensile strength per strip, while market results show tensile strength of a completely formed Geogrid. Discussion. Due to the low tensile strength obtained with the low and high density polyethylene strips, and due to the market information obtained only with polypropylene, it was decided to only take into consideration the results obtained with the polypropylene strips. Geogrids from both manufacturers are made with polypropylene geosynthetics and have ultimate tensile strength of 20 and 15.7 kilonewtons per meter, according to ASTM D6637. This Geogrid model is often used to provide base course reinforcement and subgrade stabilization. It is considered that if a single strip of reused polypropylene was able to resist 6.08 kilonewtons per meter alone, a properly assembled Geogrid made of reused polypropylene should be able to withstand a more competent amount of force. Thanks for watching.